Hi, everyone. Today I'll be discussing some work I've done with colleagues at Arizona State University and the University of Leeds using seismic data from Antarctica to map ultra-low velocity zones beneath the Southern Hemisphere. This work has been funded by both the National Science Foundation as well as NERC. Ultra-low velocity zones are anomalous patches that have been identified, at least in some locations, above the Earth's core-mantle boundary, as shown here in the map on the left. As their name indicates, ULVZs are characterized by reduced P and S wave seismic velocities and generally also show an increase in density. That said, a wide range of ULVZ characteristics has been reported in previous studies, and that, coupled with where we do and do not see ULVZ evidence, has led to many questions regarding the origin of these anomalous features. I'll also point out from the map here that investigations of the Southern Hemisphere are particularly sparse. Therefore, to expand ULVZ investigations, we've employed data from the Transantarctic Mountains Northern Network, or TAMNet, a station map of which is shown here on the right. So specifically, we're looking at PCP phases recorded by TAMNet, which are phases that have bounced or reflect off the core-mantle boundary. If we zoom in on this little pink box, this is what's shown in B and C here. And as you can see, when a ULVZ is present, we get the normal PCP phase, but we also get pre- and post-cursor phases caused by reflections off the top of and reverberations within the ULVZ layer. So we can model these pre- and post-cursors to look at the ULVZ structure. An example of this is shown here on the right. The black trace is the observed PCP data. The blue dash trace is a synthetic created with the preliminary reference Earth model, which does not contain a ULVZ. And the pink line is a synthetic based on a ULVZ inclusive model with these characteristics: a 20-kilometer thick ULVZ with an S and P velocity reduction of 30 and 11% respectively, and a 20% density increase. So this ULVZ inclusive model allows us to better fit this precursor signal indicated by the arrow. So taking the same type of analysis and applying it to all of the PCP TAMNet data, we get the results summarized here in panel A. I will note that we also apply certain quality control criteria to define both robust and more uncertain, though possible, ULVZ evidence. So each dot here represents the average PCP reflection or bounce point on the CMB. If the dot is red, that indicates robust ULVZ evidence. If it's yellow, it's more uncertain, though possible evidence. And the colored rectangles separate our results into different geographic families. In B, you can see the corresponding ULVZ characteristics we've obtained with our modeling. Again, the S and P velocity reductions and the thickness of the ULVZ. And as you can see, these characteristics vary quite a bit across the study area. So coming back to the bigger scale question of what causes ULVZs, we also looked at geodynamic simulations such as that shown here on the left. In these simulations, we introduced tracers as a proxy for subducted materials. So the tracers are introduced in the shallow mantle. We let the model run for about 200 million years, and we look at where they end up. So what you're looking at here, the colors indicate the concentration of tracers, or if you will, the accumulation of subducted materials along the core-mantle boundary. And you can see this material is kind of everywhere, though with variable accumulation. So combining both this observation from our simulations, along with both our and previous ULVZ investigations, we would argue that ULVZs are primarily associated with subducted materials. This also leads to kind of an intriguing idea, again, based on this broad scale subducted materials we see and the widespread ULVZ evidence from both our and prior studies, that ULVZs may actually be ubiquitous along the core-mantle boundary, but they just may be too thin to resolve in some locations. So I know this was a very brief talk. If you're interested in finding out more about our study, I would point you towards our recently published Science Advances paper. The DOI can be found here as well. Thank you.